Alrighty, welcome back to 353. So today's lecture, an important one, even though it's the early morning. This effectively serves as a primer for your next lab. This will probably be harder than your next lab because we're running a bank today. Ooh, fun. So, also feedback forms posted for the course and syllabite. Please fill them out. Also, it seems like, well, next week I'm traveling. Seems like the popular vote is for me to not pre-record lectures. Instead, just do a 2-hour review session closer to the exam date since we're on the last day in the morning. Joy. So next week, very likely, March 20th and 22nd will be canceled. So that is the housekeeping for today. So other than that, let's run a bank. All right, this is the fun lecture. So little setup. It's a simulation, so we are a bank, and our job is just to handle doing 10 million transfers. So how the simulation works is we can create a varying number of accounts, and each account has a unique identifier, just going to be an integer for us, and then a starting balance. So each account is going to start with $1,000. So if we choose to create, 5 accounts, we'll be managing $5,000 with our bank. And the way the transfers are going to work, they're a bit silly, but when we generate transfers between random accounts, we're just going to transfer 10% of someone's current balance to another account. So the only other rule is that they have this function that says, kind of simulates securely connecting to a bank that we assume is independent if we have threads before starting a transfer. So the rest is a coding example. So we are going to try and parallelize this to make it go vroom vroom fast. So of course we will probably encounter data races, deadlocks. Our goal is to make it go fast, and I will need your help. So this is another one where the whole thing is the exercise, so the template is in the Parallelization Example directory in the materials one that you have access to. So you can go ahead and try this again, but afterwards, and try and recreate everything we did. But we will be able to solve this in less than 50 minutes, and this is probably easier than your lab-ish. Or no, this is harder than your lab, so you should be able to do the next lab in 50 minutes. Boom. All right, great. So let's get to it, and we will even include time reading the code. So here's our code. There's a few defined. So we define our starting balance as $1,000, number of transfers as 10 million. Then we're going to try and create 8 threads to try and parallelize this. But let's see what we have first. So we have a struct account. To represent the account, each account has its own identifier, and then a balance. They're both unsigned integers. And then we have a few global variables, so number of accounts, and then this pointer to the account struct, because, well, we're just going to create a giant global array, and we're going to malloc it, and that is how we access the accounts within threads if we choose to do threads. So there's a securely connect to bank function. We assume it's independent, and we do not read it. So the other functions are the transfer function. So it takes, this is the main one. So it takes an account from and then account to. So how it works is it does securely connect to bank. Then we go ahead and we're taking 10% of the balance. So it's the same as taking the current balance from the from account and just dividing by 10. So that gives us 10%. And then that is the amounts we are transferring. So we subtract it from the from accounts balance and then add it to the to accounts balance. So from the bank's point of view, we're just moving money around. We shouldn't be losing any money here, right? Yeah.
Sorry, could you say again where the code was posted?
It's in the materials directory. Did I not push again? All right. It's there now. All right. Okay. So we have, I thought I pushed it. Okay, never mind. Sorry about that. All right, it should be there now. So here we have a run function that we set up per thread. Right now it's empty because I'm not going to create any threads, and we have a check error. Well, this will be able to check errors for the pthread functions. If it returns 0, that means no problem, so we return. Otherwise, we'll just print an error message. We will be perfect programmers today, so this should never return an error. Then how main works is checks for 2 arguments, so the name of the program and then the number of accounts to use. It does a set locale thing, so we just have commas for our numbers, so they're a bit easier to read. And then, well, we try and, convert the input to a unsigned integer. We do some error checking to make sure that I did not type anything stupid. Then we go ahead, figure out the account size, so it's the number of accounts times the size of the structure. We go ahead, malloc it, print off the memory used in megabytes, because this can get bad. And then for each account, we're just doing this without threads to make sure we don't have any data races. So we just assign a unique ID, so they're just one indexed, and then start each account at our starting balance, which is just $1,000. And then our initial bank funds should just be the number of accounts we have times 1,000, right? So if I have 5 accounts, I'm managing $5,000. So let's skip this for now. And then here is our loop. That is the main thing we want to parallelize. So it just loops for as many transfers as we want to do, picks a random account from as an index, random account to 2, and then it'll initiate the transfer. So it'll just access the struct at that index and then just take the address of it because this function just wants pointers. And then that is the main thing we want to parallelize. After this, we're going to just do this serially. So we're going to make sure that our total balance across all the accounts hopefully matches what we started with. So we take the total balance, we go through all the accounts and sum up the current balance at the end. And if we are running a good bank, we should have the same amount of money that we started with. So let's get an initial time here. So we'll do bank sim, say we're doing 1,000 accounts. So we're managing $1 million. So 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7, Okay, it took a while. It took like 10 seconds. So our goal is to make that faster. So as my first step, what should I do to make this faster? Get rid of the for loop? Not quite. Like very, very high level, how do I want to make this faster? Yeah. Threads, right? So this just has one thread going, so this machine has more than one thread, so I could be doing 8 things at a time, right? So why don't I just use threads? So that commented out code is just to set that up. So I want to parallelize this for loop. So here, I'll just uncomment this. So this will make 8 threads, set it up. We'll have a thread ID if we need it. Turns out we probably don't. Then afterwards, it'll wait for them all to join. So wait for all the threads to finish before we serially check what the account balance is to make sure we don't screw anything up. So this is what I'm doing in each thread. So should this go faster now? Did I just make things go vroom, vroom 8 times faster? So let's see, let's compile it. Do, 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 do. That's a Jeopardy thing, right? I don't know why that's in my head. Wow, this sucks. What was my big issue here? Why is this so much slower? Yeah. Context switching. Not quite. So think about, with one thread, how many transfers was I doing? I was doing 10 million, right? Now I have 8 threads. How many transfers am I doing? Yeah, 80 million. Do I want to do that? No. So how should I make this? Wow, it's still going, eh? All right, good thing I plugged in my laptop so it doesn't die. So that was over a minute. So what should I do to make sure that I still have 10 million transfers in total? So I should have the same amount of work. So if I have 8 of you to help and I have 10 million transfers, do I just tell all 8 of you to do 10 million transfers? How many transfers do I tell you each to do? Yeah, just an eighth of the work. You all do an eighth of the work, right? So if I'm doing this per thread, I want to make sure I do the same number of transfers in total. So I just take the number of transfers and divide it by the number of threads. Now I should correctly have 8 threads. Each are doing an eighth of the work, right? All right, am I done? Is this a perfect program that'll just go 8 times faster? Any guesses as to, anyone want to tell me why this is bad? Yeah.
The threads might just be doing the same transfers.
The threads could be doing the same transfers, but in this case, the 2 random numbers it gets, they're going to be different per thread, so should be okay, yeah. So there might be a slight thing where the number of transfers is not divisible by the number of threads, so we might get, turns out this one is perfectly divisible. If it wasn't, then one thread may have to do 1 extra transfer, but for 10 million, not that big of a deal. Yeah.
Could there potentially be data races if 2 threads are trying to transfer between the same accounts?
Ooh, potential data races, right? If threads are all running at the same time, there's nothing to protect these accounts. They are just all in memory, and we don't really know. So let's see. So we might have data races, so let's run it with our 10 or 1,000 accounts. We start with $1 million, and then we run it. Shit. Oh yeah, we made money. All right, great. So that's how, yeah, now we're the government, right? Hell yeah. So, yeah, this is how finance works, right? So, okay, well, we lost money now. Okay. Well, finance sucks. I want to quit now. So, nice thing about this, well, let's see if we do, I don't know. Let's pretend we're a small bank and we just have 10. Stonks. We made hella money. All right, this is great. I like this. So, do you think, whatever the Canadian equivalent of the Federal Trade Commission would enjoy this? If you just suddenly claimed you had $10,000 and now you have, I don't even know what number that is, a big one. So, we have some problem here, and it is data races. And, unlike most problems in computing, whenever we had the problem was smaller, our problem was bigger. Because let's say I'm a gigantic bank and I'm managing 1 million accounts. So I'm managing, what, $1 billion? So we know that there's data races, but if I let this run a little bit, boom. So this is an instance of we are now too big to fail. So we can, if we ever screw up, we can just get a bailout, right? Whew. All right, so how would I go about fixing this? So I have a data race. How do I prevent said data race? Yep.
Some sort of lock or semaphore for mutex.
Yeah, so for data races, primarily we want to solve them using mutexes because we just want to make sure only one thread can write at a time. Here, well, our problem's mostly in this transfer function. So we can kind of see what we have a data race with, right? So we are subtracting from one account's balance and then adding to another, and this plus equal means we're going to do a memory read, we're going to increment something or decrement something, and then we're going to do a memory write, and we have multiple threads all accessing the same memory. In this case, that would be the balance of some accounts. When we had a lot of accounts, the likelihood that two threads were accessing the same memory at the same time was fairly low, so that's why we got a good answer. But when we just had 10 threads, the likelihood was very, 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 very high. And in which case, when we ran this, pretty much every time we start with 10 grand and then we get some absurd number. So we are more likely to have a data race. In this case, it's an unsigned integer, so we just essentially underflowed it, and it wrapped around to the highest number, and we got some ridiculous number. So we want to solve this using mutexes. So, okay, well, simplest thing to do that is safe is maybe I just static pthread mutex, whoops. So I just create a mutex. Oh, I should initialize it, pthread initializer. Let's hope I spelled that correctly. Okay, so how do I prevent data races with just this big ass mutex, or just one mutex? Okay, well, so easiest thing to do with the monitor is like if I just do a lock. So let's say I lock it. Okay, so I was lock before, lock after. Do I have a data race now? Are we awake this morning? So, yeah. Yeah, no data races. Is this a great idea? Yeah.
Not necessarily, because it seems like you don't have the advantages of parallelism anymore.
Yeah, so this is basically what all my threads are doing. This is like the bulk of their work. And if I just have one single mutex and I lock at the beginning, and then I unlock at the end, it means only one thread can do this at a time. So why the hell am I even using threads at this point? All right, so if I compile and I run that, I'll stick a time on here, but I'm guessing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, as soon as it gets over 10, it's a bad idea because 10 was what I got when I just had a single thread. Oh, it actually finished. All right, we got 21 seconds of real time, but the system time was 55, so my computer worked really, really hard to get that number at the end, so it was way worse than just having a single thread. So I could make it a little bit better because I told you that the securely connect to bank function is independent per thread, so I could move the lock down. So now all 8 of my threads could be executing this at the same time, and it could be doing that in parallel. So I would expect a bit better performance with that, but here I have to lock the whole thing. Otherwise, I'm pretty much screwed and I have a data race. So how should I make this perform better? Yeah. Yeah, maybe I make one mutex per account. That's a good idea. So I just make sure that 2 threads cannot go ahead and change the balance of the same account at the same time. So what I could do here is, well, in the account, maybe I just create a mutex there. So let's just call it mutex. I will get rid of this. So now each account has a mutex for the account. So now in here, well, now I should probably lock both of them. So I should do a mutex lock on the address of from mutex, and then lock the 2, and then unlock to unlock from. All right, should that be safe? Okay, so this is it. All right, so we got, if this is safe, we are done in 20 minutes and we can go home. If it's not, we got some work to do. So let's go for 1,000. We'll time it. 1, 2, 3, 4, 5, 6, starting to get worried, 7, 8, 9, 10. Okay, we're worried. Okay. What's happening? This is taking a long time. And this is like helping other people debug it. So help, my program does not work. It freezes. Yeah. Did a deadlock happen? Is it possible for this to deadlock? It looks like I got my mutexes in the same order every time. How would this deadlock? So I always get the from one and then the to one, right? Anyone think of a situation where this could deadlock with 2 threads? And let's make sure it was a deadlock. So we can look at our process monitor and see how hard our CPU is working. Right now, all my cores are pretty much idle. So that pretty much tells me I'm not doing any work. So likely I do have a deadlock. Yep. Two simultaneous transfers are trying to go between each other. So like thread 1 is doing a transfer from, I don't know, let's say account 1 to 2, and then thread 2 is trying to do like a 2 to a 1. Yeah, is that what you were going to say too? Yeah, okay. So in this case, we could have a deadlock, right? So in this case, thread 1 would go ahead, execute first. It would acquire, in this case, from. So this would be from. This would be to. So remember, these are pointers. That doesn't mean we're always accessing things in the same manner. So we have from could be thread or account 1. So we could lock account 1's mutex, then context over to thread 2. And then we could go ahead and it would try and lock account 2's mutex, and it would do that. And now we're screwed. Both threads are waiting on each other's mutexes. So if we go back to thread 1, it would try to acquire account 2's mutex, which thread 2 already has. And if we try and execute thread 2, it tries to acquire account 1's mutex, which thread 1 already has. So we are screwed. And there's another comment about a read-write lock. So in this case, a read-write lock won't help us either, because it would still deadlock, because we would have to lock it as writing, because we have a write here. We have to ensure mutual exclusion. Nothing's really just reading. All right, so I have a deadlock. How fix? And I'll also show you a cool little tool. Oh, look, see, I killed it after 3 minutes. So there is you know how you use Valgrind for memory errors and it's useful? So turns out there is a tool to help you with thread errors, and it is called Thread Sanitizer. So in the next docs, I'll have instructions for how to use it, and it should run for you on the website. But I can just rebuild my project using thread sanitizer, and it will add some additional checks to my code for me to make sure I do not screw up my threads, and it will check for data races and deadlocks and all that fun stuff. So now if I run my bank sim, oh, I have to compile. So now if I run my bank sim, it really, really yells at me. It says lock order inversion, potential deadlock, and it tells me what happened. So if I scroll up, it turns out my deadlock is pretty big. So this is it will show you the loop of locks. So someone acquired mutex 400 or 750, which acquired that, 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 da 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 da, and this big list, and then eventually some thread that had this lock was trying to get lock 750 that was already acquired here. So turns out that my cycle was pretty big. That caused my deadlock. So it just wasn't 2 threads involved in it. This was like all of my threads got found, and it got very angry at me, and it told me essentially where all my things are. And fun note, if I just got rid of these, so let's say I don't have them anymore. So when I didn't have them anymore, well, I didn't have deadlocking issues, but I had data races. And if I run that, it just yells at me that there's potential data races. So this tool will only detect things that happen when you actually run it. So just because it's clean doesn't mean that your program is 100% correct. But if it detects an error, there is a 100% chance that there is an issue with your program. So it only actually detects things when it runs. So it is not 100% of the time, but it is a fairly good and useful tool. So I'll just get rid of it for now, because it will, like Valgrind, like really, really, really slow down things. Okay, so back on track now. Woo, my laptop's getting warm. All right, so how do I prevent a deadlock here? Yeah.
Could you try like splitting it up so you're only using one lock at a time? Like you lock the from, do the operations, unlock it, and then lock the to, do the operations, lock that.
So if I do something like this, oops, like this, right? So this, so if I do this, let's see. So this one shouldn't have a deadlock because one thread only gets one lock at a time. So seems to work, but there is a slight issue here where we might not have like consistent numbers between the transfers. It's like a really subtle difference if we have this scenario, because this just ensures there's no data races between adding and subtracting amounts between accounts, but the actual remaining balance in the accounts might not be what we expect if we just did it one by one by one, because this can essentially do half the transfer instead of the whole thing all at once. So our customers might not get what they expect, but we as the bank are happy because, well, if the bank's out like $1, you'll get a lot of emails, but if the bank screws you out of like $100,000, they have no idea what happened and can't help you. So in this case, from the bank's point of view, we are good, but there is a slight issue where the amount the customers have isn't quite right. So let's rewind again. Oh, then there's another comment. We can add a lock for the two mutexes to ensure the two lines run together. Maybe, but that's weird. how would I solve this? So each account has an ID, right? So how do I make sure that my accounts are, I always get the lock in the same order? Yeah.
You could use the try lock function.
Yeah, one option is that I could use try lock. So maybe I do that first. So I would lock my mutex, and then what I could do is I could try to lock the other one. So I could do a try lock. So I could try to get the 2's mutex, and then in this case, if I successfully get it, oops, try lock. If I successfully get it, then this will return 0, and we'll just go out here, and everything will be good. Otherwise, I don't have the lock, and I should just try and get it again, right? So should it just look like this, or what else should I write? Yeah. Yeah, put a sleep in there or a yield. So if this was your lab 4, we'd do like a what yield. So it turns out there's actually a yield in Linux, but it is older than, wow, I can't type. Was it sched yield? So it's called sched yield and not anything else, although I'm pretty sure I typed that wrong. Sched yield, okay. So the yield for the Linux kernel is just called sched yield. That will run anything. How did I type that wrong? Oh, I can't spell yield. All right, great. So I just yield if I don't get the lock. Is that good? All right, well, we can run it. Bank sim, let's do 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 do. I have screwed up my bank. All right, great. So looks like things are still running, but not all of them. So I should have, 8 cores all working, and currently I have 4 all trying really, really hard, which means they're probably just stuck in this while loop. So this while loop's just going over and over and over again, and they're trying really, really hard. So that did not quite work. Yeah?
You didn't release the first lock.
So I did not release the first lock. So I should unlock it before I go to sleep, right? So the from. All right, so that's it. Should work now? Yeah.
I think you should also put, I think you should try to lock it again, lock the from mutex again after the yield.
Yes. I have to lock it again after the yield, like this, right?
Yeah.
Same thing? Yeah. Yeah, so I need to lock it again after the yield because I want to yield with no locks held. And I want to break out of this loop with both locks. So in this case, if I make it past this line, I have the from mutex. So I try to get the to mutex. If I do get it and this returns 0, I just go this line and boom, I have 2 locks. If I don't get it, well, I only have the from mutex, so I unlock it. Then when I yield, I have no locks held. And then after I come back, well, I wait until I acquire the from mutex again, and then I try and get the to mutex again. If I don't get it, same thing happens. If I do get it, I run this line with both locks. All right, so now my code looks great, right? No problems? We've solved everything? One, 2, 3, 4, 5, 6, 7, concerning, 8, 9, not good. All right, some clues here. Ooh. So I seem to be retrying an awful lot. And if I count them, 1, 2, oh, that one switched. Oh, we're switching. 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 threads. They're all at 100%. And my laptop is a good thing it's plugged into the outlet. So what is my issue here? Why essentially are all 8 threads trying over and over and over and over again? And this one's actually pretty subtle. So I will give you a hint. Did I write any code to make sure that the from account is not the same as the to account? No. So what's happening if it's one thread is trying to transfer to and from the same account? So it means the mutex is the same, right? So if the mutex is the same, well, could lock it, no problem. Will it ever be able to acquire the other lock? No, right? So turns out if I'm trying to transfer from and to the same account, well, that's stupid. I'm in net zero, nothing's actually going to happen. So I could actually just check if the pointer is the same. So if it's the same pointer, in this case, it means the same account. Otherwise, if I want to be smarter, maybe I just check their IDs are the same. If I want to be, I don't know, more generic or something like that. So if I'm transferring to and from the same account, maybe I just return. I just don't do it because nothing's going to happen anyways. All right, am I good now? Do we have the greatest bank in the world? Well, let's see. 1, 2, 3, 4, 5. Hey, we seem to work. Doesn't really go any faster, but doesn't go any slower either. And it actually works. Yay, yep.
Would it make it faster if when you made the call to the random down in the main function, if you checked there if they were the same, because then you'd only be calling transfer for valid transfers?
Yeah, so I could make sure that here that to and from index aren't the same. Turns out I don't care. Oh, also turns out I missed something that makes this actually slow. So oh right, that's why I have thread ID. Okay, so turns out that, well, rand is a thread safe function and each thread is using it. So they can only run one at a time, so it makes sure that that doesn't have any data races. Turns out there is a version of rand that is actually independent per thread. So if we look it up, rand, okay, that is not what I wanted. So if we look up rand, it tells us that there's rand and there's srand. And then there's also this rand-r, which is apparently deprecated, but we're still going to use it anyways. So if we bother to look at all of them, it says that, okay, well, these are all thread safe, which is great, but this rand function uses like an internal seed that it makes sure it doesn't have any data races between all of them. And it turns out if we use rand-r, then rand-r, we can just set our own seed and then go ahead and make it whatever we want. So we can go ahead and just create a seed that's just, I don't know, we can do it based off the thread ID. We can initialize it as the thread ID, and then we can just change rand to rand-r and do that. In this case, I'm not going to care if the accounts to and from are the same. Just I'll have it behave as it did before. Whoops, wrong symbol. So now if I compile and run that, oh, whoops, unsigned int seed, unsigned. Compile, all right, we're clean. So now if I run my bank, boom, look at that speed.
So does the rand function make sure that they're not the same number, or how does it make sure that you're from two accounts?
Oh, this does not make sure that the from and to accounts are not the same. So I still just have the check right up here that they're the same.
Oh, so this just simply makes it faster than the original.
Yeah, so this was purely for performance because that rand function, well, like when we were using rand, took like 10 seconds because it turns out a lot of the time was just spent getting IDs. And well, since it was thread safe, essentially rand, the implementation of it would just have one mutex and lock at the beginning, unlock at the end. So only one thread can do it at a time. So it turns out if we just used rand instead of this rand_r, things were way, way, way slower because, well, only one thread can call rand at a time. Turns out that generating random numbers was actually a lot of this. So now when we run it, we have a very, very, very fast bank. So that's almost 8 times as fast. We had to solve some problems, and it was a little painful, but at the end of the day, if you can make your program go 8 times faster, probably a very, very good thing that people pay you money for, then this is why they hire you. So if you didn't take this course before and you just threw threads at it, well, it's not going to work. Maybe if you're working for, I don't know, name, insert big bank here, it might work for a while. And then, you know, maybe 1 or 2 times the balance is off, and then, well, as long as you don't lose money, you don't care. All right. Also, let's see, comment. ChatGPT said we could also use thread pools. Will it make it even faster? So in this case, we only create 8 threads and then have all 8 of them just do all of the work. So we don't need thread pools. Thread pools are generally when you have really, really small tasks. So instead of creating like 1,000,000 threads that each do one very, very small task, the idea of a thread pool is I only create 8 threads and then I have like a queue of tasks and I have all the threads just kind of work together to chew through all of those 1,000,000 small tasks instead of making a new thread for each one. But in this case, we know all the work each thread needs to do ahead of time, so we don't need to use thread pools. And if you did it for this, that would be silly. So, great. Any other problems with our bank, or have we now created the best bank in the world? Yep.
Can we try for the 10?
Oh, 10. Yeah, so our problem was like 10 was really bad. 10 works. But, curious. Seemed to get a bit slower. What about if I just have only 5 accounts? Okay, well, a little bit slower too. Let's see, 3. What's a good number? Seems to get a bit slower. Why is it getting slower the fewer accounts I have? Yeah. Yeah, so if I have fewer accounts, more likelihood that 2 threads are going to be using the same account, in which case there's that magic word contention. So they're all trying to compete for the same lock. Only one can get it at a time. So it will be slower the less threads we have. Yeah, in this case, we only have 3 accounts. We don't need nested while loops or anything silly like that. So this works. If I wanted to, I could also make sure I acquire mutexes in the same order. So if for some reason I didn't like this try-lock one, well, we have IDs So what I will do is we can go ahead and ensure an absolute order on the locks. So if from ID is less than to ID, then maybe I acquire the from mutex first. So let's go ahead and create mutex. I'll call it a pointer. I'll call it M1. And then we will also create M2. And then if the from ID is less than the to ID, I'm always going to acquire the lowest one first. So I will assign M2 or M1 equal to the from, M2 equal to the to mutex. Ooh, that looks ugly. Let's get rid of this. And then in the other case where, well, the IDs can't be the same because we checked at the very front. So in the other case, we'll just do the old copy paste a Rooney and flip these. So we'll do something like that. So in the case that the to ID is actually smaller than the from ID, well then I'll assign M1 equal to the to and M2 equal to the from. So turns out if I do this, M1 is always going to be the lowest ID. So I can go ahead and then I could now do pthread. I could just lock M1 and then lock M2. And then here I can make sure, doesn't really matter. Oh, wait. And then here I can just unlock them both. So now I have a definite order. And if I go ahead and I run this, let's go back to 10. So if I run this, it works too. For some reason, it is much slower. So probably due to the lock contention. So let's go up to 1,000. Yeah, and then it's pretty much as fast. Joy. So we could implement it both ways. We can go ahead and sanity check that we are all good. So we could use thread sanitizer, compile it, and then run it. So it'll be much slower. Whoops. Oh, I didn't compile it. So it'll be much, much, much slower because it's checking that we don't have any data races. It's checking that we don't have any deadlocks or anything like that. So we can let it run, but we should be fairly confident at this point that it's run for a while now and hasn't yelled at us. So that's probably pretty good. And this new one does not deadlock because we always acquire locks in the same order. We always acquire the mutex from the account with the lowest ID first. So we always do M1 followed by M2. And here, well, if the from ID is lower than 2, then M1 is from, so we would get that one first. Otherwise, if the to ID is less than the from ID, then we get 2 first. All right, so we can be fairly confident it's working because it hasn't blown up on me yet. But like I said, thread sanitizer does a lot of checking and is slow. So how slow? Very slow, but it seems to work. All right, yeah. Yeah, so some of this, like performance-wise, maybe I had more locking, and then I was like, oh, well, it doesn't make sense to use threads if, I don't know, I have a crappy CPU or something with only a few cores. So you could have a check for that, but checking that is going to be very, very hard because you don't know what anyone's going to run their computer on and like how fast the cores are, things like that. So there's always going to be trade-offs. And the answer is you just have to benchmark it yourself and see if it's worth it. Because until I fix this, well, it was slow until I actually changed this rand function. and then it got like 8 times faster. So just something you have to keep track of and monitor because there's no right solution. It's just like, how much can I actually run in parallel? If I can't run much of it in parallel, threads probably aren't worth it. So any other quick questions before you wrap up? I think that's it. All right, so yay, that's lab, was it, 5. So you can do lab 5, joy. So just remember, bone for you, we're all in this together.